Hello everyone and welcome. Today we have joined forces with Ardena to be able to bring to you the webinar on linking solution chemistry to crystallization. My name is Carmen Guguta and I'm your host from Technobis Crystallization Systems today, together with René Steendam, the project leader of Ardena.
So the science part of my crystallization of my presentation is on linking solution chemistry to crystallization, and this is a really broad topic. So I will focus on a few things, namely primary nucleation, but I'll also discuss secondary nucleation, solid phase transitions, and mechanical properties of the final API. And the main compound that I will discuss is Pregabalin, which is also known as Lyrica, which is made by Pfizer. So why would you need solids? Why is it interesting? So APIs in solid form have a lot of benefits, including patience, acceptance, processing. For instance, it's easier to process solid than a liquid. And usually physical and chemical stability are also enhanced if you have it in solid form. So there are a few ways to crystallize. One of the most applied in industry is crystallization from solutions, since it is widely applicable. It's generally simple because you only need a solvent and you can basically do the crystallization process. It's cost efficient, and usually also you have purification. So unreacted starting materials or impurity tend to stay in solution, and usually your API selectively crystallizes from solution. And then we have a few methods at our disposal for solution crystallization. Cooling crystallization, which is the most applied one in industry, and I will talk about this in more detail. But in case you have a compound that is thermally labile or does not have a good concentration relationship with the temperature, you can also opt for anti-solvent evaporative crystallization or reactive crystallization. So for cooling crystallization, the start usually is a solubility phase diagram. In this case, we have on the vertical axis the concentration of your API, and on the horizontal axis the temperature. And the line in the graph is the solubility, usually denoted as C star. And as you can see, usually the concentration increases with temperature, or the solubility. Another term that we often use in crystallization is the supersaturation or the supersaturation ratio, and that's defined by C over C star, and that tells you something about the driving force for crystallization. So typically with a cooling crystallization, you start out with a heated solution, which is completely clear. So you're on the right-hand side of the solubility curve. And that's where you have an undersaturated solution. So your concentration is lower than the solubility line, and you don't have any crystals in your system. The supersaturation is below 1. But then if you cool down, you pass the solubility line and you end up in the metastable zone, and your system becomes supersaturated. So your concentration is now larger than the solubility, and the supersaturation ratio will also be larger than 1. So here you have the driving force for crystallization. So what happens then? So if you have primary nucleation, the molecules in your supersaturated solution agglomerate into dimers, into trimers, into tetramers, and so on. And this is actually a reversible process. So some of those agglomerates tend to become larger and larger in size, but others also tend to become smaller and completely dissolve again. And this is actually a random process, a Monte Carlo process. So it's a roll of a dice, basically, until at some point you have crystallization. And this is called primary nucleation if it occurs completely from solution. And after that, you actually already have formed a new phase. And this phase can act as a new template for further crystallization. So what happens usually is that molecules from solution, they grow onto the surface of an existing crystal. And because of shear forces or impact, the new layer is removed from the original crystal, and they will nucleate in the bulk as well. And this is called secondary nucleation. And after that, the surface of the crystal becomes free, and it can be used again for another round, and so on. And also, of course, the newly formed crystals, they also form as new templates for crystallization. So usually primary nucleation really starts at the beginning. Secondary nucleation takes over at some point, and usually the supersaturation in the end is depleted by secondary nucleation. This is very abstract, so I'll show this first with an actual experiment. So in this case, I show an experiment involving sodium chlorate, which I used in the time when I was in Ireland. And sodium chlorate is a very nice compound because it is achiral in solution, because it has no chiral center. But in the solid phase, it can actually crystallize into a left or right-handed helix, making it chiral in the solid phase. So I denote this by either the blue or the red form. So if you would do a crystallization experiment with a fairly high supersaturation, you will get this again, this Monte Carlo process, and at some point you get primary nucleation. And since we applied initially a low supersaturation, you only have one primary nucleation event, which is immediately followed by secondary nucleation. And in this case, if you have a chiral system, the chance of crystallizing the left or right-handed form, the blue or red, is 50-50. So in this case, I show red, but it can also be blue. And secondary nucleation is followed, and that usually proceeds through copying the identity of the first crystal. So in this case, you get more of the red. And this is indeed what we saw in the lab. So this graph shows time on the horizontal axis, the temperature on the left-handed axis, and the counts measured by FPRM on the right-handed axis. So we cooled the solution to supersaturation. We waited for crystallization to occur. And then immediately after crystallization, we isolated the crystals and looked at between the polarized light microscope and found that all crystals were of the same color. Hence, all crystals are of the same chirality. But if you apply a much higher supersaturation, then still you would have the same process, but you have more than one primary nucleation event. So in that case, theoretically, you would form both chiral forms. And that's indeed what we observed. As you can see from the graph, we now have both light and dark colored crystals, whereas with the low supersaturation or with induction time, we have only one colored crystal. So the take-home message here is controlling primary nucleation is essential. So what's the theory behind primary nucleation? So primary nucleation has, in principle, two theories. The oldest one is classical nucleation theory. It's actually a quite simplified theory, but in some cases it actually works to explain roughly the outcome of the experiments. And in this case, it describes it by taking into account a single molecule that becomes a cluster in solution, finally later a crystalline nucleus, and in the end, a full-grown crystal. And this theory takes into account that the cluster in solution has the same structure as the final crystal. But more recently, a second theory has been hypothesized involving the density fluctuation of molecules in solution, and those become a liquid-like cluster, so still no order in the liquid. And over time, this disordered cluster becomes an ordered crystalline nucleus. And finally, it removes the solvent around it and becoming a crystal in the end. And this is called the two-step nucleation mechanism. And it's more elaborate than the classical nucleation theory. So if you would like to know more about these theories, I would refer you to this nice Angewand review. And for the talk, I will focus more on the classical nucleation theory, since I also use this in my studies. So for the classical nucleation theory, we have this key expression. It shows the J, which is the nucleation rate, so the amount of particles formed per volume per time, depends on a kinetic parameter A, and that tells you something about the molecular kinetics of nucleation, and thermodynamic parameter B, which reflects more the structure of the nucleus. And also it depends on the supersaturation ratio. So if you go back to the schematic depiction that I showed earlier, initially the reversible process of forming complex monomers, dimers, trimers, and so on, this depends really on the kinetic parameter. And usually processes involved in this involves that the sulfated state, so on the left-hand side, loses a sulfation shell, undergoes a conformation change, and then finally gets absorbed in the growing nucleus. And then finally, the transition from a nucleus or from an associate into a nucleus, that's defined by the thermodynamic parameter B, and that's actually defined by the gain in bulk free energy versus interfacial energy. So the bulk free energy is positive, whereas the interfacial energy contribution is negative. And at some point, they cancel each other out, leading to crystallization. And B captures the molecular packing motif and tells us something about the interaction between a nucleus and solution. So the case study of my webinar is Pregabalin. So Pregabalin is made by Pfizer, also better known as Lyrica, and it's among the top 20 prescription medications. And it's used to treat epilepsy, generalized anxiety disorder, and is used in a lot of pain treatments. And last year it actually lost patent, so it's now generic. So here's the chemical structure. It's a gamma amino acid, zwitterionic, so it has both a positive and negative charge side. And it's chiral as well, so it's manufactured as the S configuration. And in terms of structure, it actually is very similar to L-leucine. And before we started working on this project, the only data that was known on this compound in terms of solid state chemistry was that it was only present as an anhydrous form. The only downside of this anhydrous form is that the material is very brittle. So here's an SEM microscopic picture showing large particles, and as you can see on the surface of the particles, it contains a lot of fines. So even if you touch the material on a glass plate under a microscope, it already breaks apart. So this is a really big problem for manufacturing processes. So we were interested in investigating this compound to elucidate basically the crystallization of this API using the classical nucleation theory, and see how the solvent choice impacts the crystallization of this API, and perhaps to come to a better form. And I should mention this, this work has been done in Limerick in the SSPC, so the Synthesis and Solid State Pharmaceutical Center. So for the classical nucleation theory, one way to use this theory is to use induction times. So induction time means that you have crystallization at a fixed supersaturation and a fixed temperature. And if you apply these conditions, then the time depends on when you have crystallization, and that's called the induction time. So what you do is you have clear solution, for instance, an HPLC file. You make it slightly supersaturated by cooling. You have a laser, and then if you have a detector as well, you will see that the transmittance is about 100% because it just goes through. Then you wait, and at some point you have primary nucleation. Usually this is not immediately detected, but usually nucleation also triggers secondary nucleation. The file rapidly becomes a cloudy suspension. And in this case, the cloudy suspension will block the laser light, and the transmittance will go down below 100%. And that's when you know, okay, we have crystallization. And since nucleation this way, crystallization is is a stochastic process, you need to have many induction times to use it in the classical nucleation theory. So we collected those those induction times with Crystal 16. Graphically, it looks something like this. So we have on the horizontal scale the time in hours. On the left-hand side in blue, temperature and the transmissivity, so the amount of laser light that's passed through the vial, isn't shown in green. So typically you would heat up until everything dissolves, cool down until you have a saturated solution, a supersaturated solution, I should say. And then you wait until crystallization occurs. And here you can see crystallization occurs quite rapidly in the beginning. And in the second experiment here at 5 hours, you see also again crystallization occurs quite rapidly. Here around 20 hours, you see that a slightly longer crystallization time is needed, but you see that it's that a lot of time is actually lost because once you know the induction time, you can actually move on to the next experiment. So what we used in our experiments is a feedback loop, also part of the Crystal 16, where we started the next experiment when the transmissivity was below 90%, so when crystals were present. And that way we could actually significantly reduce the experimentation time. And that way we could do a lot of experiments in a small amount of time. For our work, we performed in total more than 1,800 crystallization experiments within a month. And we tested 5 solvent systems, and that way we could obtain 50 to 160 induction times per supersaturation per solvent. So if you have all that data, typically what you would do is rearrange them into a probability figure shown here. So here you see the probability of crystallization as a function of crystallization time or induction time. And the different colors denote different supersaturations. So the red color is a low supersaturation, and the orange color is the highest tested supersaturation ratio. And in this case, water was used as the solvent. So at the low supersaturation, you see that after 15,000 seconds, about 50% of all vials have crystallized. But if you look at the other supersaturations, if you go slightly higher, then you see that the chance of finding crystallization at a higher supersaturation becomes 100%. What's interesting here is that in water, we notice in combination with pregabalin that a small supersaturation was needed to already induce nucleation, but also the range of supersaturation was quite narrow. Because if we looked at another solvent system that we tested, namely methanol, we noticed that a much higher supersaturation ratio was needed for crystallization, and also the range of supersaturation was much wider. So already at this stage, we noticed, okay, there is something going on with the solvent choice. So once you have all this data, you can actually fit it to this formula, which shows the probability as a function of the nucleation rate, J, the volume of your reactor, V, is a constant, T is the induction time, and the Tg is the growth time of a nucleus. And the nucleation rate and the growth time you can get basically from fitting this equation to the data. So in the graphs, you see the line that's actually the fit from the data. And also, if you want to know more about this approach, there's also a webinar from Joop de Horst, also on the Technobiz website, that explains this in more detail. So here are 5 solvents that we tested. We basically use water and water, methanol, and IPA mixtures. Because it has limited solubility in all other solvents. And we expressed the molar fraction of water here in this column. So water is, of course, 1. And then you see it's being reduced as a function of methanol or IPA. And we also use pure methanol to have a system in which we don't or hardly have any water. So here we also noticed that if we decrease the amount of water, the driving force for nucleation has to become higher. In other words, water facilitates crystallization of the API. The growth time of a nucleus, which we could calculate using the classical nucleation theory, also is much shorter in water, so easier to form. And in methanol, it's much longer. So there's also a relationship here. And then if we plot the ln nucleation rate over S, ln J over S, against 1 over ln S, we can get kinetic parameter A and thermodynamic parameter B from the intercept and slope of these plots. So I use color coding here, so water is shown here, and then the other solvent systems are shown on the left-hand side. And from that data, we could also estimate the effective energy needed to create a surface. So this is also, again, a sort of energy barrier to form a crystal. And you can see that in water, the barrier is not so high, but becomes higher if you have less water in your system. But what's really surprising in this case is that although we see significant differences across our experiments in all observations, if we look at the final product, we always obtain the anhydrous form, which is present in literature. So this at this stage, we thought, okay, maybe the two-step nucleation process is involved rather than classical nucleation theory, or we form a metastable precursor before the anhydrous form. So we went a bit deeper into the classical nucleation theory, and we looked at the kinetic parameter and thermodynamic parameter and used them to calculate a few things. So in this graph, you see the different solvent systems. So on the left-hand side is pure water, green. And then if you go to the right, less water is involved in the system. So pure methanol is shown on the right-hand side in blue. And here on the horizontal bottom axis, you see the supersaturation going up from left to right. And what we did is we calculated molecular kinetics by using the kinetic parameter A to get a value for how easy it is the molecules associate in solution. And you see in water, the value is quite high, so we have to look at the open symbols. But if you reduce the amount of water in the system, the kinetics become much lower, around 0. And also in terms of thermodynamic parameter, we noticed that this change was dependent on the amount of water in the system. So the thermodynamic parameter here, we express this as B. We can calculate the number of the number of molecules in the critical nucleus. And that's shown on the left-hand side in the graph. And you see in water, it's the number of molecules involved in the critical nucleus means that it's a large cluster. But if you go to the right, fewer molecules are involved in the cluster. So the size also appears to be water dependent. And this is something we could actually measure. So for that, we used dynamic light scattering, DLS. And this way we could look into solution of different water fractions. So for instance, in pure water, we noticed that the particle size distribution, or actually cluster size distribution, is quite big, shown on the right. But if you add more methanol to the system, you see that the cluster size distribution becomes smaller. So this is another experimental confirmation that indeed the water fraction depends or influences the structure of the nucleus in solution. But then still, how is it possible that we still obtain an anhydrous form as shown by XRPD? So an additional measurement is what we did in this case, namely with Raman spectroscopy. So we followed the process by inline Raman. Here you see the graph of it. So we looked at this particular wavelength window. And initially we have the solvated form in the system, as shown as the broad peak here. The structure of pregabalin is similar to elucidate, and that way we could actually assign the functional groups of pregabalin to the peaks observed by Raman. And we noticed after a time that nucleation occurred, and we saw this because the shape of the peak became much narrower, and also it became a bit lower. And we saw also in the crystallizer that particles were formed. And then after a while, we noticed that a second peak emerged, which is probably indicative of the hydrate form, because the peak on the right-hand side could be assigned to the alkyl chain. And on the left-hand side, we have the carboxylate group. Initially, you don't see it because we think water is coordinating to it. So it's not really vibrating. But afterwards, in the anhydrous form, it's free to vibrate. So therefore, you will see this peak coming up. And basically, this time between hydrate to the final anhydrous form is the conversion time from the hydrate to the anhydrous form. In water, this time is about 100 minutes. But if you have a water methanol mixture, for instance, 1:1, this transition time is much faster. But in the end, we of course wanted to have a single crystal of this hydrate to really confirm that it's indeed a hydrate form. And Uday actually was able to do this. So first he revisited the structure of the anhydrous form, and what you can see from this structure is that the zwitterionic groups are coordinated towards each other, but the alkyl chains stick towards each other, and they form a very much interlocked system. And because it's such an interlocked system, the molecules are not really free to move, and therefore the material is quite brittle. But here you can see the structure of a hydrate form, which was obtained by freeze drying from water. And what you can see is that the water molecules actually coordinate to the carboxylate group and to the amine group. And that way the molecule reconfigures itself. And as a result, the alkyl chains cannot interconnect with the second layer. So you have more room for movement. This is also reflected in a second form that was obtained, form 2 of a hydrate, which is very similar in structure, but slightly different. And this is because the layers can freely move over each other. And this is called slip planes, so they can slip over each other. And as a result, you have bendable crystals instead of brittle crystals. And this behavior was not only observed for pregabalin, but also for gabapentin, which is also a gamma amino acid with similar pharmacokinetic behavior. Gabapentin has actually more forms. So on the top right, the top 3 are anhydrous forms, and the top bottom 2 are hydrates. And as you can see from the micrographs here, if you manipulate the crystals, you can actually make bendable crystals for both pregabalin and gabapentin. And we can use this also to explain what we see in our crystallization experiments. So initially we form in water the hydrate form, and because water distorts this crystal structure, the second layer cannot really move into it. But if water is removed, the alkyl chains rearrange themselves, and therefore a gap emerges, and a second layer can easily fit into it. And this will make the anhydrous structure, which is very brittle. And the thing is that the hydrate is formed easier in solution, as we saw from the kinetic data. But in the solid phase, this transition into the anhydrate is irreversible because water cannot really easily come into the structure and make the hydrate form anymore. And it's also metastable. But the hydrate form is actually a bendable crystal, which is quite nice to have, especially considering the brittle nature of the anhydrous form. So how do you still obtain a stabilized form of the bendable crystal? So again, Uday and others, including me at UL, we looked at the pregabalin, the brittle structure, and instead of introducing water into the system, we looked at a coformer or a counter ion, which could take up the place instead, and that way perhaps make slip planes as well. So a small screen involving a few counter ions and coformers was tested, and only with oxalic acid and salicylic acid a nice salt was obtained. And this salt was analyzed further. So again, here you have the crystal structure of the anhydrous form. So it's a very much interlocked structure, or what's called an interdigitated structure. So no movement. But with the counter ions, we do see the same behavior as we saw with the hydrate. The counter ion also in this case orients itself or connects with the carboxylate groups or with the amine groups. And that way distortion of the alkyl chains occur, and therefore you will get slip planes. And the same behavior was observed with salicylic acid. And as a result, it was possible to bend the crystals, and it was able to spell the letters of the pharmaceutical center this way. And what's more, the multi-component systems also have favorable physical properties in other terms. For instance, the tablability. So in this graph, you see the tensile strength as a function of compaction pressure. So at the bottom, you see pregabalin. So it takes only a little strength to already break the tablets. But for the other multi-component systems, especially for the oxalate salt form shown at the top, you need a lot more strength to break the crystal, which is usually favored in pharmaceutical processing. And also what's usually the case with salts is that you have a much higher solubility in water. So here in this graph, you see Pregabalin, which is the red below, in the graph below. You see that the solubility is quite poor in water, but if you have the salts, they are much higher and also much more temperature dependent. And if you would like to read more about this work, you can find it in crystalline.com. And also all the work that I've used in my presentation, the links are shown at the bottom of the slides as well. So in summary, I showed how crystallization of pregabalin works. So initially we looked at crystallization of pregabalin from different solutions, and we always obtained the anhydrous stable form. However, this form was brittle. So we investigated the behavior and found that actually a hydrate can be formed as an intermediate unstable form. But it had many good properties, including a bendable nature. And since at some point we figured out the mechanism of this transition, we were able to crystal engineer it into a salt which is stable at room temperature and also has the good physical properties of the hydrate.